It has this structure. Well, I don't remember the bond structure at the moment because without the bond structure, there's no point in saying that it's going up and down. But it has these two configurations. It has these two configurations that cannot be obtained from one by just a rotation by 180 degrees. This is not a rotation.
So what is it?
I don't remember now. I mean, the thing I remember is that it's not due to rotation.
Okay.
So, but then there are these molecules which are not mirror images of themselves. That, as if I'm not wrong, this is one of them. If they are not mirror images of one and the of themselves, you cannot just rotate them to one another. The so-called chiral molecules. But then, when I try to understand it with my knowledge of chemistry, it does look like it doesn't look like that. So I'm not so sure why. But I remember that these two configurations are not equivalent to each other. So this is another two-state system. So we have state 1 and state 2. And furthermore, if you have, for example, the Hamiltonian will be, well, those two configurations, they will be degenerate. There is a finite transition between the two states. You can diagonalize this Hamiltonian by the states, let's say the symmetrical state and the anti-symmetrical state. And the Hamiltonian acting on the symmetrical state will be epsilon 0 plus delta, the symmetrical state. And the Hamiltonian acting on the anti-symmetrical state will be epsilon 0 minus delta. Again, if you allow me to make a claim from my mind, let me change these deltas to -1, so this is minus, this is plus. The anti-symmetrical state should have a higher energy. Now, the reason why the anti-symmetrical state should have a higher energy is basically, you should just consider the nitrogen. The wave function of the nitrogen atom itself. Let's just assume the hydrogens are fixed. Then what is the wave function of the hydrogen? The symmetrical wave function will look like this. This is the midpoint. The antisymmetrical wave function will look like this. So the probability of observing the nitrogen at midpoint for the antisymmetric wave function will be 0. But if you look at that antisymmetric wave function, its derivative is large. That means it has a large kinetic energy. So its energy will typically be larger. Also, if you consider any system that you have studied in quantum mechanics, any eigensystem, the ground state is always a Gaussian. The first excited state has one node. The higher energy states always have higher number of nodes. Basically because the more nodes you have, the faster it oscillates, and hence the larger the kinetic energy. Now, each one of these systems have an electric dipole moment. So if you put these in an external electric field, they will have a additional energy given by this. Now you see what happens if we have a constant electric field. No, sorry. Well, let's not repeat what we had done already before. You see, this electric dipole moment this time will basically be proportional to the position of the nitrogen. You see, if you look at the hydrogens, although they are at the edges of a triangle, well, they are highly symmetric. It's an equilateral triangle. So the contribution to the electric dipole moment comes from the nitrogen, mainly. So that's why the electric dipole moment is proportional to the position of the nitrogen. So, well, now basically we have a two-state system which are non-degenerate. It couples to an external electric field. And if you take more or less are back to the previous problem. Now, of course, if you want to put in more detail, this electric dipole moment vector in each one of these states this will be 0. Why? Because of parity. You see, under parity, symmetrical state goes to the symmetrical state, anti-symmetrical state goes to the negative of it. So this one basically because the symmetrical state doesn't change, but even if I put if I do the same thing for the anti-symmetrical state, it's the same because I get -1 squared. But this is minus the electric dipole moment. So a number that is minus the same number is basically 0. Similarly, this is also 0. But this one and the other one so again, we are back to the same problem. We have a two-state system. These two states are degenerate. There is an energy shift between them. And now we have a potential, even a time-dependent potential if you have this as a time-dependent electric field, which couples the symmetrical and anti-symmetrical states. Yes, question.
I couldn't understand why if this is not 0, but this is 0.
Well, you see here, could you follow this argument over here?
Okay. position.
Now these two, you see, let's do the same analysis for this one. Well, this is equal to, it's the same thing. Under parity, symmetric state doesn't change. Antisymmetric change state acquires a minus sign, so parity acting on the antisymmetric state, if I multiply it with a minus 1, I get the antisymmetric state. But at the same time, electric dipole moment, because it is proportional to the position of the nitrogen, it changes sign. So this is equal to it just says that that matrix element is equal to itself. Before, for the diagonal cases, what we showed was the matrix element is equal to minus itself, and hence it had to be 0. But for these off-diagonal elements, the only thing I can prove is that that matrix element is equal to itself.
So both diagonal elements are not 0. So both diagonal elements are not 0.
They don't have to be 0. Well, it might happen that, I don't know, for example, it might happen that they turn out to be 0. But there's no reason for them to be 0, and in general, they will not be 0. And in fact, if you write them out, this is 1 over 2, 1, which notation did I use? Yes, 1, 2. 1 plus 2, 1 minus 2, 1 minus 2, yes. Plus, minus 2 plus 2.
Minus correct.
Well, parity will just change 2 to 1. Up to a phase which I can choose to be 1. But that means that this is equal to and there is no reason for these two terms to be equal to each other. In fact, I would expect them definitely to be not equal to each other.
No, parity of 2 to 1, parity of 1 to 2. Do they pick up the same phase?
Now, p squared has to be 0. Sorry, 1.
1, yeah.
So in principle, I can put an eta over here. And let's say here, then I will get 1 over eta.
So they get different phase. They will get different phase. So we can choose one. Oh, if you choose one, it's the other one is also one.
Okay, there can be different phases, but keep in mind that also this should be 1. This here, I think this is enough to make sure that that term is equal to this one.
Sorry, you got rid of the 1 over 2 factor outside?
Yes, because this term is equal to this one, this term is equal to this one.
But don't you know those two terms are 0 to begin with? First two.
First two terms, no, they are minus each other.
Oh, right.
You see, if the electric dipole moment is due to the nitrogen, if the nitrogen is up, the electric dipole moment will be pointing up in the first one. And in the second one, the electric dipole moment will be pointing down. So I'm subtracting these two terms.
But didn't we just conclude these were diagonal elements of 0?
No,
For
depends on which basis you are talking
sorry,
about. You
okay,
see, before I was the two-state system that I will be studying will be the anti-symmetric state and the symmetric state. Not these states. Not these two states. These are 1 and 2. In the basis the basis that is made up of the symmetric and anti-symmetric wave functions, the H0 is diagonal, but V is off diagonal. So we are back to our initial problem, where we have a diagonal H0 and a time-dependent potential. Of course, if you change the basis, it looks different. Now here I went back to the position basis, if you want, the position of the nitrogen basis, eigenstate basis. So again, this time it's the electric field. In the NMR case, we are using the magnetic field. This time it's the electric field. Using the electric field, well, basically you can do two things. One is just think about the Stern-Gerlach experiment. What to do? You apply a non-uniform magnetic field, constant in time. So you split the states. Well, the same thing will happen over here if you have a non-uniform electric field, constant in time.
Is it a non-uniform field in Stern-Gerlach?
No, yeah. You see, uniform magnetic field doesn't exert any force on the magnetic dipoles. If you have a uniform magnetic field, the force acting on magnetic dipoles is 0. Well, the same thing for the electric dipole. You see, electric dipoles is, in the simplest term, you have a positive charge here and a negative charge here, and they have the same charge. If you apply a uniform electric field, both positive and negative charges will feel exactly a force of exactly equal magnitude, but opposite direction, so they cancel, there is no net force. But if you apply a non-uniform electric field, there will be a net force acting on the dipole. And furthermore, these symmetric and anti-symmetric states, they will be feeling a force in different directions. Take these ammonium molecules, send it through a region of constant electric field, constant non-uniform electric field, constant in time. They will split into two. So initially you have a symmetrical and anti-symmetrical ammonia. You split them. Take the anti-symmetrical one. That they have higher energy. You block the symmetrical one. You put them in a region of space which have a external time-dependent electric field that is oscillating in time at the resonance frequency. So arrange this length L such that what you get at the end is the symmetrical state. You see, if you apply an external electric field, external driving force, we had already at resonance, we had seen that if you started one state, after some time, after some distance, if you want, it will be completely in the other state. So you start with the higher energy state, then you obtain a lower energy state. Well, before we said that the emission direction was arbitrary. Take this to be a resonant cavity, so that you force a definite mode of the emission. So what happened to the energy of this ammonia molecule? Well, it will be emitted, it will be transferred to the external electric field, electromagnetic field, and so what you have obtained is a maser. Just like the laser, but in the microwave. Why the microwave? Well, that is the energy shift between these two states. Well, the basic idea is essentially the same.
So, two questions. One, so we can also do the reverse, right? The symmetric would.
If you want, yes.
Long path and
Depends on what you would like to do. Do you want to extract some energy from the system of a given frequency, or dump energy to the system?
Okay.
You see, for example, in lasers, what we want to have is extract energy from electrons. In accelerators, what we would like to have is give energy to the electrons.
Stupid question. Does that mean the resonant cavity gets colder? Does the resonant cavity get colder?
Well, you see, why should it get cold?
The energy is coming. If we have symmetrics, if
Yes.
we have the lower energy state flipping to the higher energy state, it's gaining energy from the electric field.
Which energy?
Our
At which frequency, let me ask?
resonance.
Yeah, but thermal energy, you have all the spectrum.
Right.
You are absorbing only one of them, if it exists in the region.
Sure. Yeah.
So, for example, if, let's say that the temperature of the cavity is such that there is some significant energy at that frequency, yes, that will be absorbed, but that's just a single frequency that will be absorbed. The general shape of the spectrum of the electromagnetic radiation in the cavity will not change.
The electromagnetic field loses energy to our ammonia molecule.
Only at the given
Only
frequency.
at a given frequency.
So that after the ammonia molecule leaves, it won't be a thermal distribution to start with.
No, but doesn't it affect the electromagnetic field's passage through the cavity? Doesn't it affect the EM field's subsequent motion through the cavity? Or is the resonant cavity a vacuum?
How will it affect?
I mean, you're cutting out some frequencies, right? You're
Yeah, I mean, you basically, if you have this spectrum before, after the ammonia passes, you will have, I don't know, let's say that this frequency, this spectrum. Not much really.
Second question, this is a bit off topic, but could you just comment on the Zeeman effect? Is the Zeeman effect occurs even with a uniform magnetic field, right?
Yes.
Splitting spectral lines. So why do we need a non-uniform magnetic field for?
You see, here the question we are having is the energy transfer.
Right.
What happens in the Zeeman effect is if you apply, if you put an atom, for example, in a magnetic field, the energy levels split.
Right.
That's the only thing that happens. Are you transferring energy?
No.
Not really. But of course, if you transfer energy in some other means, by some other means, in that case, you see that splitting. But what you are seeing is the energy levels, the actual energy levels. So, for example, what you do is you take an atom, put it in a magnetic field.
Right.
Well, the energy levels will split. There is nothing to observe there.
That's-
Then you have to excite the atoms. How do you excite the atoms? You apply an external field. Well, typically you will excite it to a much higher energy,
right.
and then randomly they will decay. So then they can decay in these split states, either to one of them or the other one. So when you excite the atoms, look at their decay, you will just see these two lines in the spectrum. That's a completely statistical effect. Now here what you are doing is you are doing something more controlled. What we are having is you have this two-state system. And this tells me that there is a particular wave that I can effectively transfer energy to it and extract energy from it. So that's the basic difference. But even if you think of the Zeeman effect, the experimental setup, you shine laser light. You apply an external field that gives you the splitting of the energy levels, then you shine laser light. That's your external time-dependent field.
Right.
But that doesn't happen in the resonance, because you are not actually looking at the transitions between these two split states.
Splitting happens without any energy transfer.
Yeah, the splitting is there. But
Okay.
you see, energy levels, if they don't contain any electron there, there's no energy there. When you are talking about energy levels, you are basically talking about the possible values the energy the electron can have.
Right.
In principle. If there's no electron there, well, there's no energy to talk about.
Okay. So we just eigenvalues change. Possible eigenvalues.
Yes, possible eigenvalues change that. And then the other problem is, how do you observe those eigenvalues? That's treated as a separate problem.
Okay.
Here our question is transferring energy to a system and taking it back. That's, for example, basically what you also do in lasers. You have to somehow give it some energy so that you excite the atoms, but you are also trying to extract the energy in a particular form, in a way transforming the energy. So here we also have another system where you can give energy to the system and take it back. And of course, this giving energy to the system and taking it back would be just sending photons to our system, typically, and observing photons that come out. And then, you see, the resonance frequency, you see, we all said that the resonance frequency is proportional to the splitting in the energy levels. Well, typically the splitting in the energy levels will be inversely proportional to the mass of the whatever object has that two-state system. So by measuring the resonance frequencies, for example, you can determine the mass distribution. Or let's say, for example, different nuclei have different masses. So the nuclei of different atoms will have different resonance frequencies. So let's say you shine light. You send some electromagnetic radiation, you apply some time-dependent field to there. And let's say that time-dependent field is resonant only with the hydrogen. Then you look at every point, you take a picture, if you want, sensitive to this splitting, sensitive to the photon that will be emitted by this transition. You take a picture, and you see that from certain points there is more light coming to you than from certain other points. Well, that tells you that where the hydrogen is localized.
I mean, yeah. You study spectroscopy.
Yeah.
Yeah.
But hydrogen is localized, for example, on tissue in your body, not in bones. You don't get much hydrogen in the bones or in the liquid. So you can see where there is more liquid or more bone structure, and you can see where you have a tissue sample. And even in the tissue, you can determine the density of the tissue itself. So whether there are some dense regions or less dense regions, you can determine them. So that is used to visualize the body without cutting it open. Other.
So can you please go back to the Stern-Gerlach schematic? What's our starting point here? We're sending a mixture of symmetric and anti-symmetric states.
Yes. You take your ammonia gas, you send it through this non-uniform electric field which will split them.
Right.
the symmetrical and anti-symmetrical. Just block the low energy one. If you want to extract energy from the system, let's say, block the low energy one, you have the high energy system. You send it to a cavity where you see you don't even need to send any external field there. You see, you send these ammonia molecules into this higher energy ammonia molecules into that cavity. Let's say one of them randomly just goes down. Well, that creates an external time-dependent electric field resonant with the resonance frequency of the ammonia. And of course, you have to make sure that that is one of the modes of your resonant cavity. So when you start one of them, well, that you have the external resonant external field that just forces all of them to lose energy in that cavity before they leave. And you just make sure that the size is such that at the moment they leave, all of them has lost their energy. And now, if before you didn't have any radiation in electric, any photons in the cavity, once you send those, you get them at a particular frequency. In a sense, this is like playing the flute. You blow the air, you excite the modes in the flute. Here you send the ammonia molecules, it excites the resonances in the resonant cavity, but those resonances at the same time forces the ammonia molecules to lose their energy. So all of them lose their energy.
And of course, we could do the reverse process simultaneously, right, to the other state.
Depending on what you want to do. Here I would like to have a system of microwave radiation, coherent microwave radiation.
Okay. We have a beam of ammonia gas at the beginning. I send it to the system. We get a maser on the one side. On the other side, the opposite process happens.
What do you mean on the other side?
You have to block those.
If we don't lock the symmetric states,
Okay,
they could also do the opposite, right? Just flip up
sure.
to resonant cavity.
But they are not actually, are they specially, these SNA states are specially separated?
Yes,
Are they?
just like the Stern-Gerlach experiment. They interact differently with the external field.
There's a net total energy, what I'm trying to get at. There's a net total energy at the beginning. My anti-symmetric states lose energy, go to a low energy state. My symmetric states gain energy. I'm having trouble keeping track of the energy, that's all.
You see, I have a mixture of molecules. Some of them have a lower energy, some of them have a higher energy.
Alright, yeah, fair enough. Some gain, some lose, and the net is the same.
No, I mean, I have this system.
Okay.
Some molecules have lower energy, some molecules have higher energy. Then I separate these lower energy ammonia and the higher energy ammonia. I dump the lower energy ones. The higher energy ones, I make sure that they lose their energy. They lose energy. And the difference in the energy is now in my microwave radiation.
No, that's fine. I'm saying if you don't dump the low energy ones,
Okay.
you make them gain energy.
Why should?
I mean,
Now,
we just do-
let's say that
Huh.
if you want to make them gain energy, you have to apply an external field there.
After the splitting, okay.
After the splitting, you have to apply an external field on the symmetrical state.
And that's what
And they will acquire energy from the external field. Well, the lower one, you don't have to apply an external field because they will create their own external field anyway once they enter the cavity.
Okay, now I get it.
So there's no problem with energy conservation. Other questions?
I am concerned about spatial separation because I don't think we did anything to suggest that they are spatially separated.
Well, you see, if you have an electric dipole in a non-uniform electric field, they will have different, they will feel a force.
Symmetric one and
Symmetric and anti-symmetric ones will feel a different force. because their dipole moments will be different. Since they feel different forces, they will move differently in this external electric field.
Do they have different electric dipoles? Can you show that? Because I know about state 1 and state 2 have different dipole moments, but symmetric and unsymmetric states are linear combination of them, so, and they have the same intensity kind of noise variability.
Well, let's see.
I'm thinking they have the same electric dipole moments, but I'm not so sure.
Now, how can we calculate the force?
E times mu.
Hmm?
E times mu.
Now, E times mu is not the force.
So we have E is same for both of them. So we just have to check if mu is same for symmetric and
Well,
unsymmetric.
let's see. Mu electric dipole moment
Mhm.
for the symmetrical one. Similarly for the anti-symmetrical one. Both are zero. That's why I'm not so sure if this treatment is correct to obtain the force.
Mhm.
You see, the problem will be okay, so you see, the problem will be if you apply a non-uniform electric field, parity is not a symmetry of your system. That will also cause a problem with this argument, with our arguments leading to these being zero.
Yeah, but even if it's not parity, E is same for both
Hmm?
states. Even if it's not parity, E is same for both states. So the force is still the same. Like this.
Now, E, you see, if E is the same for both sides, there is no force anyway.
Or-
There is a force only if E is not the same for both sides.
I can understand.
That is the non-uniform case.
I was considering that
Hmm.
he is like
You see, let's see.
anything same on both states, but if it's
Now,
not,
if you have this state,
actually state 1 and state 2 has different dipole moments. But-
let's say this has a dipole moment. We said that this has a dipole moment proportional to the position of the nitrogen.
Mhm.
Let's say that this has an electric dipole moment in this direction. Okay. So the force acting on this will be non-zero if E is non-uniform. The force acting on this one, I'm sorry. The force acting on this one will also be non-zero if E is non-uniform. Now the question is, if E is non-uniform, what is the force acting on this one? Yes, I would just go ahead and, let's say, define some force operator, whatever that is. Then look at the matrix element. Well, this would be the first thing I would try. Let's say this will be equal to 1 over 2 f11 plus f22 plus f12, no, plus or minus f21. So I see that at least if f12 and f21 is non-zero, the force will be different for the two states. One comes with a plus sign, those two terms. One comes with a minus sign for those two terms. In fact, I would expect f12 and f21 to be the same.
Sign difference? Or no?
Let's see. Well, you see, if you have a uniform force, you see that these two have, as you said, a sign. Sorry, here there is a minus sign over here. No, okay. But this, the force being a vector, this is what I would obtain.
Where is there a minus sign? Where is there a minus sign?
The force is a vector, it changes sign, direction.
How about the change states? So I told you.
Sorry, okay. So there's no minus sign over here, we are right. So if this is so here we get a minus sign. So then you can say that f12 and f21, they cancel each other. But if there is a non-uniform electric field, the force will not be symmetrical.
Yeah. So this is why we say
Well, as I said, it doesn't come to me how to calculate the force acting on these particles in the case of non-uniform fields quantum mechanically. But this would be my first guess in approaching this problem. Okay, so we don't have any more time to look at the perturbation theories. That is for one day. You already?
We can continue if everyone has time.
Well, your friend probably had to leave.
Absolutely.
My daughter is waiting for me at home.
Sorry, what are we doing next time? You said put something about.
Well, you see, we obtained this result. We found the exact result. We started saying that we are looking at time-dependent perturbation theory. Well, there's no perturbation here. We are looking at exact results. So let's look at it, the perturbation.
Transition rates and things like that.
Yeah. Well, probably I will leave it as homework though,
Oh, okay.
because I would rather look at sudden approximation, adiabatic approximation.
We have you left this as homework because in our homework problem we have a sudden approximation problem. I think we have a sudden approximation problem in the homework already.
Okay,
So I think
so
you've already left this as a homework.
no, I will discuss it on Monday.
Okay.
So you can listen to trying to apply. When you will be listening to the lecture in your mind, you will concentrate because you want to solve the homework.
Fair enough.
In fact, that sudden approximation is kind of easy. You see, if you are looking for your state at the time t plus delta t, well, you can just do a Taylor expansion if you want. A Taylor expansion would just tell you that this is psi at the time t plus delta t times derivative of the state at the time t with respect to time. But this is nothing but the Hamiltonian up to a coefficient. So the change in the wave function is very small as long as delta t is sufficiently small, no matter what happens to the Hamiltonian. For example, you might change your Hamiltonian suddenly, but during that sudden change, since if delta t is very small, well, your wave function didn't have time to change. Well, of course, we have to be more precise on what does it mean to have a sudden change, for what does it mean to have delta t very small. But once we define those things, well, this tells me that if a change in the Hamiltonian happens suddenly, the wave function does not change. That's the idea. So then it is now an initial value problem. You have your new Hamiltonian, and you also know your initial wave function, because that is the wave function you had before the perturbation. But we will be more precise on Monday.
Master kuantum muydu hocam?
Doktor